We are going to start today with section 9.7, formal charge. And formal charge is defined as the number of valence electrons, that's the number of valence electrons, minus the number of outer electrons around an atom. So we're just looking at single atoms. So it's the number of valence electrons on an atom, or for an atom, minus the number of electrons around an atom. And as an example, we're going to look at carbonate. We're going to look at each atom separately. And when we talk about electrons around an atom, it's not all of the electrons. It's the electrons that are actually touching that atom if we look at the Lewis structure. So this oxygen right here would have 1, 2, 3, 4, 5, 6, and 7 electrons that would be assigned to it. So this one would have 7 electrons. Let's check all of them. This oxygen right over here would have 1, 2, 3, 4, 5, 6 electrons assigned to it. 6 electrons. And this oxygen right over here would have 1, 2, 3, 4, 5, 6, 7 electrons assigned to it. And the carbon in the middle, this little happy carbon here, would have 1, 2, 3, 4 electrons assigned to it in the Lewis structure. That is really a lot of mess in there. So I'm just going to circle. We've got 7 electrons, 6 electrons, 7 electrons, 4 electrons. Now, we have the equation for formal charge right up here. So, for carbon, carbon has how many valence electrons? We're looking at valence electrons. It has 4 valence electrons minus the number of electrons around the carbon or assigned to the carbon. That's this 4 right here, minus 4 electrons, is 0. So the formal charge for carbon is 0. Now, these oxygens, let's look at the oxygens. We have 2 different kinds of oxygens here. We have the ones with the single bond and the one with the double bond. So we're going to look at the oxygens that have O's, oxygens. That looks really strange. Oxygens that have 7 electrons. So those oxygens, we'll call them O sub 7 for 7 electrons. Oxygen has how many valence electrons? How many valence electrons? 6 minus, I'm just using the definition of formal charge. 6 minus, these have 7 electrons assigned to them, that is -1. So those oxygens have a formal charge of -1. Now the O's, actually it's not plural, there's only one O. The O that has 6 electrons around it, so that O, well, O has how many valence electrons? 6 valence electrons minus 6 electrons assigned to it. So that O has a formal charge of 0. Let's redraw this. Okay, I've redrawn the Lewis structure and I'm going to put the formal charge right near each atom. So the carbon has a formal charge of 0. The oxygen right here has a formal charge, that was the one with 6 electrons around it, has a formal charge of 0. This oxygen has a formal charge of -1, and this oxygen has a formal charge of -1. Notice the formal charges, when you add them all up, 0, 0, -1, -1. So the total formal charge here is -2. They should always add up to the total charge of the ion or the element or the compound. If there is no charge in the compound, then the formal charges have to all add up to 0. Okay, So here is a problem for you to do on your own. You're going to figure out what the formal charge is for each atom in each of these elements. And I'm also going to do it, so you want to go ahead and pause right now if you want to do this on your own, and then just fast forward to where we end up. Don't forget when you're doing it, make sure you do that little boundary, because the bond, one electron of each bond belongs to each of the two atoms. So there's two electrons in the bond. One belongs to one atom, one belongs to the other atom. Okay, so I'm going to do this. Go ahead and pause now if you want to do it on your own. So this oxygen right here has 1, 2, 3, 4, 5, 6 electrons assigned to it. 6 electrons assigned to it, and that atom, oxygen, has 6 valence electrons, so the formal charge of this oxygen right here is 0. Okay, this oxygen down at the bottom, 1, 2, 3, 4, 5, 6, 7 electrons assigned to it, and that oxygen should have 6 electrons, but it has 7 assigned to it, so its formal charge is -1. And I'm going to use a different color, -1. This one is 0. Okay, the oxygen over on the right has 1, 2, 3, 4, 5, 6 electrons assigned to it, and oxygen has 6 valence electrons minus 6 electrons assigned to it, formal charge of 0. 0 right there. And now let's look at the oxygen at the top. It's got 1, 2, 3, 4, 5, 6, 7 electrons assigned to it. But oxygen should only have 6 valence electrons, and that one has 7 electrons assigned to it, so the formal charge on that oxygen is -1. Okay, oh, sulfur, we forgot to do sulfur. I forgot to do sulfur. You didn't do anything wrong. Okay, let's count our sulfur in this one. 1, 2, 3, 4, 5, 6. So these are all the oxygens. Now the sulfur. Sulfur should have 6 valence electrons. It does have 6 valence electrons. Not only should it, it does. And in this structure, it has 6 electrons around it. 0. So the formal charge for the sulfur in the middle there is 0. That is a huge mess, but hopefully you can see the formal charges for each different atom in that ion, which is sulfate. Okay, we're going to do the other possible way to draw sulfate over on the right side. So notice all the oxygens look exactly the same, so we only need to do the oxygen once. Let's see. Oh, and we want to draw our little lines here, dividing up those bonded, the covalent bonds. Those electrons, one belongs to each atom on each side of the bond. So we'll do this oxygen over on the left. 1, 2, 3, 4, 5, 6, 7 electrons assigned to that oxygen. And oxygen has how many valence electrons? That's right, 6. And the oxygen has 7 electrons assigned to it in the structure, which would be a formal charge of -1. Now, I don't want to do all these oxygens and redo that calculation. I see they're all the same. Those are all having a formal charge of -1. Let's look at sulfur now. Sulfur has 4 electrons assigned to it. But sulfur has 6 valence electrons. Boy, there's lots of 6s in these. It's not always 6, just in the problems I gave you today. Sulfur has 6 valence electrons, and the structure has only 4 electrons assigned to sulfur. So sulfur would have a formal charge of +2. Okay, +2 on the sulfur. All right, we've done that problem. Why do we care about this? So here's the important note. Okay, right here. This is why we care. When picking between two possible Lewis structures, the more correct structure is the structure with the least number of non-zero formal charges. So if we look at these two structures, the structure on the left has, two non-zero formal charges. And the structure on the right over here has 1, 2, 3, 4, five non-zero formal charges. And the more correct structure is the structure with the least number of non-zero formal charges. So would that be the one on the left or the right? Yes, the one on the left. This is the accepted structure for sulfate. Now, this structure does not follow our rules for drawing Lewis structures. And on a test, if you were drawing sulfate, I would expect you to draw it the way I had it drawn on the right. You're not expected to memorize that this is a possible structure. With formal charges, what I do expect is if I give you two different possible structures, you should know to use formal charge to figure out which structure is more correct. Or if I just give you a specific molecule, you should be able to tell me the formal charge of each atom in the molecule. Okay, and now we're moving on to section 9.8, which is resonance. Resonance is something that occurs when a bond in a molecule can move between different places within the molecule, and now I'm about to show you what that looks like. So here we have SO3, and you should notice that in SO3 the double bond can be on the right side, on the bottom, or on the left side. Literally, that double bond can move from one place to another. So when I have SO3, it's really almost as though I've got a bond that literally moves. Okay, so I've drawn in the double bond. Notice I haven't drawn the extra electron pairs, but they are there. I can't move everything around at once. So this second bond here, it literally is going back and forth and back and forth. And now it can also go over here, but I don't know how to rotate this line here. So this bond is here, and then it's here, and then it's over here, and then it's here, and then it's here, and then it's over here, and it's just randomly moving around. That bond is literally going around and around and around. So it spends about a third. Do you notice there are three? 1, 2, 3 places where that bond can be, and that bond is constantly moving around and around. Remember, that bond is really 2 electrons. Those 2 electrons are jumping around in this molecule. Now, how much time is that bond spending in each place? Well, how many places are there? Do you notice there are 3 places? 1, 2, 3 places where the bond can be. Again, this one should be rotated 90 degrees, but I can't do that. I don't know how to use the smartboard that way. So the bond's spending a third of its time here, a third of its time here, and a third of its time here when there is a resonance structure. Now I just want to fix that resonance structure so that really those other electrons are there. And when the bond moves over to one place, those electrons move to the other place. So if that bond switches over there, these electrons go over there. If that bond goes over here, those, oh goodness, they separated themselves. Those electrons, oh, they rotated. Oh dear, I don't want to rotate them. I want to carry them. Oh, I don't know what's happening here. I'm copying and making. Okay, I was going a little crazy over there. The point is that with resonance, the bonds can move around, and they spend a proportional amount of time in each place that they could be. So that's resonance. There are many structures where resonance occurs. We did a structure in class the other day, SO2. We did this morning. SO2 has a resonance structure. Why don't you try to figure out what the resonance structure is for this one? And I'm about to write it, so if you want to do it on your own, go ahead and pause. I'm writing it right now. There we go. So SO2 exhibits resonance, and in SO2 that double bond can move to the left or the right, so it spends half of its time in each place. All right, moving on. Section 910, bond enthalpy. So, we learned in Chapter 6 about thermochemistry, and we learned that the heat of a reaction is the heat of formation of the products minus the heat of reaction, the heat of formation of the reactants. Now we're going to learn how to calculate the heat of a reaction using what is called bond energy. Now, bond energy is the amount of energy you need to put into a bond in order to break the bond. And when a bond is formed, energy is given off. When a bond is broken, we have to put energy in. So, bond broken, energy has to go in, energy in. We have to put in energy to break a bond. Is that endo or exothermic? Remember that way back when? Endo, exo? If I have to put energy in, that would be endothermic. Okay? When a bond is formed, energy is given off. And if energy is given off, we would say, is it exo or endothermic? If energy is given off, that would be an exothermic process. Exothermic. So now, if we're going to use bond energies to calculate the heat of reaction for a reaction, then the enthalpy of reaction, heat of reaction, is going to be the sum. Now, let's think. Endothermic, bonds broken. Are your reactants broken or are your reactants formed? Do we break bonds of the reactants? Yes, we have to break the reactant bonds. So the positive part here will actually be the reactants. This is the opposite of how we did this in the past. So the heat of reaction will be the sum of the bond energy of the reactants minus the sum of the bond energy of the products. And again, that's because this negative sign means exothermic, and in order to form a bond, that is an exothermic process, and it's the products that have the bonds forming. Again, this is the opposite. We have products minus reactants for heat of formation when we're using heat of formation data. When we're using bond energy data, we have to do reactants minus products. Okay, so we're going to do one problem here. We want to find the heat of reaction, delta H, for this reaction right here. Okay? Now, in order to do one of these problems, you have to first figure out what the Lewis structures are for your different compounds or pure elements in the reaction. So I've already done that for you. We don't need to recalculate those. What we do need to do now is find the bond energy. So delta H will be all of the bonds, bond energy of all the reactants. So notice we have an NN triple bond. So we're going to look up in our table. An NN triple bond is right here. So we've got 941 kilojoules per mole. We will have 941 kilojoules per mole. We have to multiply by the coefficient. There's just 1 mole times 1 mole, because there's 1 mole of NN, plus we have right here an HH bond. And how many? We have 3 moles of those. So let's look up HH right here, 432 plus 432 kilojoules per mole times 3 moles. We have 3 moles of HH bonds. Now we have to subtract off all of the products, because remember, Our equation when we have bond energy is a little different. It's reactants minus products. So we just did a reactants, now we're subtracting the products. And in the products, in each NH3, notice I have 3 NH bonds, right? But note I have 2 NH3 molecules, so I actually have 6 NH bonds because I have that times 2. So I have 6 NH bonds. So we look up NH. Where is it? Oh, there we go. NH is 391. So I have 391 kilojoules per mole times 6 moles. The moles cancel. I am left with kilojoules, and the answer is